All right, let's begin going through now molecule scoring. So to do that, I'm going to first go ahead and move some of these nodes to give us ourselves a bit of space. So I'm going to take this reaction enumeration and move it to one side so I can drag and select multiple nodes, in particular these 4 nodes, and I'm going to move them across here. And then I'm going to go to draw the structure, and there's an edge here at the connection between draw the structure and fragment-based construction. I'm just going to right click on that then and delete it. Okay. And then I'm going to take that and I'm going to move it down to the bottom here. And that gives ourselves a lot more room. All right, so we now have a lot more room to work with, and we're going to start with some post-generation scoring. Now, post-generation scoring is really about filtering, and filtering is where we usually will say 1 is a molecule we like, 0 is a molecule we do not. And often we may not explicitly do this, we may instead use, for example, deduplication strategy. Conceptually, however, it is a 1 if it's a molecule I like, and 0 is a molecule I don't like. In KNIME, this is relatively straightforward to do. So we can start by going up to the table handling section here, and then click on duplicate row filter, and then move that down. Briefly, if we click on atom-based construction, right-click on atom-based construction, go to connected to output table, we have only one column here, products. So that is the column that we're going to look into and see if there are any duplicates and remove them. So we can close the table, connect the 2 nodes together, right-click, and then go up to configure. Press configure, and this window will open, and what this is it's saying I will look inside the product field inside the table, and I will include that in my duplicate detection. And what I'll do is I will remove duplicate rows, and rows that remain, if they are duplicates, are only the first example. So if I have 2 molecules, whichever one has come first, and if they are both duplicates, the first molecule is retained. So I'm going to go ahead and press OK, right click on duplicate row filter, execute, and we can now see that this node has executed. So I right click and I go to filtered and labeled data, and we can see that instead of having 24,000 chemical structures, we now only have 16,000 chemical structures, so a significant reduction. Next, I often want to be able to remove molecules which have, for example, issues associated with liabilities. So these might be tox liabilities, they might be liabilities remaining due to reactive functional groups. One way to do this is to use what we call the RDKit molecule catalog filter. So we can click on that, drag it down, and then we can connect duplicate row filter to the RDKit molecule catalog filter. Right click on that, go to configure, and we can see here that we have, first of all, at the top, this is which molecule column to use to filter. Now, if we have multiple molecule columns, so for example, we have products or we have reagents or this type of thing coming through reaction-based enumeration, we may need to pick which one we want to filter. In this example, I care about product, the product column, and I have panes, ABC, I have the NIH, and I have zinc. So I can press apply, OK, right-click on the node, execute, and this will then remove molecules that have issues with panes substructures. So right click, and I can then go to good, and I can see that now I'm down to 10,217 molecules. And these molecules are starting to look more medicinal chemistry friendly. They're also starting to look more synthetically tractable. Now, the reason why they are more synthetically tractable is because we are removing substructures, we're removing molecules with substructures which are unpleasant or uncommon. And by unpleasant, I mean things that we know chemists will struggle to make. So if I close this table and then I actually go back to the RDKit molecule catalog filter and I right click again and go to configure, I'm going to push this a little bit further. I'm going to add Brenk by clicking at the top here, left click, and I'm going to go all the way down to Kemble. And I'm going to then press the add. So to highlight everything, I should say that you can click on one sort of row and then I can hold down shift and then I click to the bottom row, Kemble here, and it will automatically highlight all the other rows. So I can press then add, apply, OK, and then OK, right click and execute, and that node will now run. It will take slightly longer because it's got to apply more filters. So we can now look at the good molecules here after doing the more complete filtering, and we can see that there is a significantly lower number. And what this is that this is again filtering more of our generated molecules. It's scoring the molecules based upon our filters, and it is returning molecules that have a higher propensity, although no guarantee, of being makeable. And this is again all thinking about the quality of the molecules that are being generated. It's simply just removing substructures that are undesirable. Now, if there are certain collections of substructures that in your project you didn't want, then you would be able to encode these sort of substructures and then go ahead and actually use these filters to be able to then reduce the overall compound collection or compound pool that you have generated. So if we close this table now, what we can now do is calculate some descriptors. So descriptors are transforming molecules into some kind of numerical value, and we have two types here. We have the CDK molecular descriptors and then we have the RDKit molecular descriptors. So what I'm going to do is I'm going to go ahead and I'm going to first of all calculate the RDKit descriptors. I'm going to take the good molecules here and I'm going to pass them into the RDKit descriptor calculation. You'll see this little warning sign. That's because it hasn't automatically identified what the RDKit column is, so what the molecule column is. If we right click configure, we can actually set the RDKit molecule then to the product, and it will automatically then detect and do the transformation into the descriptors. A few key things here is that there are several descriptors that we have sort of pre-selected. There are many more. So to select any of these, we simply would have to click any of them that we would want. So for example, number of amide bonds, we can then press add, and that will add that descriptor to the list. We can then press apply OK, right click RDKit descriptor calculation, execute, and right click then and molecules with calculated descriptors. And we can see here that we have now more columns, and this is where we have taken our molecule, our generative molecule, our new molecule, and we have calculated the S log P, the TPSA, the fraction of sp3 hybridized carbons, and we have calculated this for the entire table. So what we could do then is we could then take these descriptors and we could calculate, for example, an MPO, or we could go ahead and filter more based upon these descriptors. So we could calculate, for example, the Lipinski rule of 5 violations and whether or not they match to a TPSA threshold. So to do that, we go up to the Lipinski RO5 violations and TPSA threshold. We can then click and drag down, and then we can connect these together. So what we can do is we can then say, okay, based upon this data, calculate me the Lipinski rule of 5 violations, and based on a particular threshold, the TPSA will say, yes, it is above, or no, it is below. So if we then press execute, right click, and then go to output table, We add some additional columns. We can see here we now have a number, which is a number of Lipinski violations. We have then a TPSA threshold check, it's false. And we also have a rotatable bond check as well. It is also false. Now, to understand where that expression came from, we can right click and we can then go to configure. And this will then load an expression, and this is the expression. So if s log p is less than or equal to 5, we would give a 0 or a 1. So this is the sort of classic Lipinski rule of 5. We then have expression 2, and this is TPSA is greater than or equal to 120. So we can then go ahead and press OK. Finally, often we want to be able to, following our generation and following our molecule scoring, we want to then go ahead and save the data. So to do that, we can go across to the download node here, and we can then move that across. And now we can connect the expression node into the download. And now we will then be able to right click, execute and open views. And what that will allow us to do is it will allow us to then download the list of enumerated molecules from the atom growing engine as a CSV. We can click that and it will then ask us where do we want to save this file. So we could save this on the desktop, we could save it into wherever we need it, and we can just go ahead and press save, apply, close, and that data is now saved on the desktop, where we could now interrogate it or use it for other applications.